kilogram object moves in one dimension. The graph to the right shows the net force acting on the object as a function of time. At time t equals to 5 seconds, the object's velocity is 2 meters per second and the object's location is 5 meters. Draw the graphs of the object's position versus time, velocity versus time, and acceleration versus time. So we are assigned question number 4, and the question presents us with a graph of the net force versus time, and we're asked to graph the acceleration versus time and the velocity versus time and position versus time. So first of all, since we're given the net force versus time, we can use this information to gain the acceleration. And we're given at first that the mass is 3 kilograms, and the net force is 9 newtons, negative 6, 0 newtons, positive 3 newtons, and between the time frames 0 to 2 seconds. We use this information to obtain the acceleration. Since we know from Newton's second law of motion, the net force is equal to mass times acceleration, which means acceleration equals to net force over mass. So dividing 9 newtons by the mass, which was 3, we'll get 3. Dividing negative 6 by 3, we'll get negative 2, and so on, and 0 and 1. So these are the accelerations we obtained from Newton's second law of motion. So since we obtained the acceleration by using this formula, we are able to draw the acceleration versus time graph. As you can see, it's accelerating at 3 meters per second squared from 0 to 2. From 0 to 2 is 3, and from 2 to 3 seconds, it's at negative 2, and from 3 to 4 is 0, and from 4 to 5, it's 1 meters per second squared. Now we have graphed the acceleration versus time graph, and we're left with the position versus time graph and the velocity versus time. And in order to graph the two other graphs, we have lots of missing components that we don't really know. So what we're going to do is chop the graph into different time frames and look at each time frame closely and figure out the missing components in order to be able to graph the other graphs. So we're going to do that by using the three famous kinematic equations listed over here. And we're going to start between the time frame 4 and 5. In the question itself, we were given that V final, or you could say V5, is 2 meters per second, and x5 is 5 meters, and delta t is 1 second. And the acceleration that we got is 1 meter per second squared. So using equation 1, V final equals to V initial plus acceleration times time. We could write it in this way. So V final is V5 and V initial is V4 times plus A times time. So we know that V5 is 2 meters per second, and V4 is what we don't know, V initial, and we know that acceleration is 1 and time is 1. So V4, we eventually get that it's 1 meter per second, so that's V initial. And using equation number 3, delta x is equal to V initial times time plus half AT squared, we get this. So V initial is 1, which we got, and time is 1, half AT squared, 1 meter per second squared, and time 1 second. So we plug in all the missing components, and we get 1.5 meter. And over here, we know that delta x is the final position minus the initial position. In this case, it's x5 minus x4. So x4 is equal to x5 minus delta x. We want to find x4. We know that x5 is 5 meters, and because we're given that, and delta x we solved for it, we got 1.5 meters, so which means we get 3.5 meters.
So now I'm going to talk about the time frame between 3 and 4. So our final velocity here equals to our initial velocity in the previous period, which was between 4 and 5. So the final velocity equal to V4, which is 1 meter per second, and the V initial, it's the one that we are looking for, which is V3, and the acceleration here is equals to 0, and the time period is, we subtract 4 and 3, and we got 1 second. So in order to get the VI, we use equation 1, so which is VF equal VI plus A times T. So we have VF here, so we plug it 1 equal Vi is our V3 here, so we just write V3, and since A is 0, so all this equals 0. So V3 equals 1 meter per second. Now using equation number 3, which is delta x equal Vi times t plus half acceleration t squared. This part will go away since acceleration is 0, as we see here. So delta x equal Vi t plus 0. Vi is V3 in this case, so V3 equals 1 and the time equals 1. So delta x will equal 1 meter, and we go to delta x. Delta x equal x4 minus x3. So we know what is delta x, and we know what is x4. So we are gonna solve for x3. x3 equals x4 minus delta x, which is equals to 3.5 minus 1, which equals to 2.5 meters.
Okay, so to find the V initial between 2 and 3, we can repeat the steps as my father did, and we use the first kinematic equation, which is V final equals V initial plus A times t, and we have the V final, which is 1 meter per second, and we have the acceleration, which is negative 2 meters squared, and we just plotted the numbers here, and we got 3 meters per second for the V initial. And to find the delta x, we can use the third equation of the kinematic equations, which is V2 times t plus half times acceleration times time squared. And then we will have 3 times 1 plus half times 2 times 1 square, and we got 2 meters. And to find the delta x, we just got we have delta x equals x minus x2, and we have delta x, which is 2 meters, and we have the x3, which is 2.5 meters, and we just solve for x2, and we have 0.5 meters.
Finally, between 0 and 2 seconds, we know that the change in time is 2, that the final velocity is 3, that the initial velocity is unknown, so we have to find that out, and that the acceleration is 3 meters per second squared, I think. So we use the first equation of kinematics, which is final velocity equals initial velocity plus acceleration times time. We do these calculations. We get that the initial velocity equals negative 3 meters per second. So now we use the second equation of kinematics. Change in x, which is position, equals initial velocity times time plus half times acceleration times time squared. We plug in our variables that we have over here. So we get negative 6 plus 6 equals 0. We rearrange what change of x equals. So we get initial position, because we want to find out what is initial position, which equals x2 minus change of x. We get that the initial position is 0.5 meters.
We came up with these velocities. We put them in the velocity and the time graph. So as we noticed, from 0 to 2 seconds, the velocity is increasing, then it's decreasing between 2 and 3, then it's constant between 3 and 4, then increasing again between 4 and 5.
We could make our position graph. The initial position is 0.5. By decreasing or increasing the velocities, we could tell if they are concave down or concave up. Here's constant velocity, so like it's a straight line.